My name is Rich Hummel. I work for AccelTex Solutions. I am from San Antonio, Texas. So therefore, I am wearing the requisite cowboy boots and camouflage that you were issued when you moved to the state of Texas. I don't know a lot of people here, so just to give you a little bit of my background, I spent most of my life as a working engineer. I started working on three-dimensional radar systems in the Air Force, moved through a lot of different technologies, got my degrees in engineering and management, and then, like a lot of people do, especially engineers, when they find out how much salespeople make, I said, you know what? That sounds like a really good idea. So I'm going to talk at a very high level about antenna design. This is really more about the things that we have to consider when we're designing an antenna so that it looks and functions the way you need it to when you're doing an installation. So, as most people know, when we're talking about RF, it's as much an art as it is a science. So this poor guy, unfortunately, he was so upset after the Donald Trump victory that we got him clay, but he really took to the paint. So he is practicing the art of antenna design. And we just lost. Come on. Huh. It's thinking about it. Is this counting against my 10 minutes? All right, so there we go. Well, just to give you a little bit of history about RF or Wi-Fi antenna design. When we first came out, when Wi-Fi antennas were first being designed, it was for a single radio, it was a single frequency, and that's pre-2000. Then we went to the early 2000s where we had a single antenna array. Okay, we were supporting two frequencies, obviously, but the elements were dedicated frequency elements. So if you had an antenna array, it would have elements 4, 2.4, and 5 gigahertz. Okay, and then you might have, depending on the AP, single or multiple elements. Now we live in the dual band antenna realm. We have a single antenna array, again supporting two frequencies. The difference is that the elements will be both 2.4 and 5 gig. And we will have, in most cases, a single antenna element per AP. It's rare, but it does happen, and I am thinking. So, there are certain things that we have to do, and we try to be awesome in our design. So what we do, like Superman, and I don't know about you guys, but when I was a kid, I thought Superman's flying was all in the cape, right? So I had to find that cape. Once I got that cape, I put it on. Once I put it on, I could be awesome. So when we talk about the things we consider in antenna design, obviously the first thing is going to be the application. Okay, what type of antenna are you going to need? Is it going to be, in general terms, omnidirectional or directional? What frequencies are we going to use? We see that the frequencies are changing constantly depending on the next release of the 802.11 standard. What type of gain do you need? Are we looking at overlapping or asymmetrical coverage areas? Beam widths today are critical. Everybody wants that sharp 3 dB edge. And antenna manufacturers are constantly trying to sharpen that edge because in high density environments, that makes your job a lot easier. Polarity, the majority of antennas out there are going to be vertically polarized. If you're in a high noise environment, you might want to consider horizontal polarization because your signal will cut through the noise that much better. Isolation between the elements. Are there environmental conditions that need to be considered? Heat, cold, moisture. All of those things combine into the different environmental factors that we have to consider. Are we talking about pigtails, or are you going to be able to directly connect that antenna to your radio? In most cases today, there's going to be a pigtail involved. Rubber ducks, really, if you're going to use rubber ducks, you're probably going to use the internal antennas. Grounding plane is always going to be important, as well as the input power. Now, the second thing we consider after the application is the type of element, okay? We all know that, again, the fact that RF doesn't always behave the way it's supposed to, that the theoretical versus the actual implementation of the antenna is going to vary. Theoretical, you could have all the numbers correct. Then you build the element, you hook it up to the radio, and you go, yeah, and it doesn't work anything like you thought it would. Is that element going to be a printed circuit board or a discrete metal component? And we also have to consider the isolation for those individual elements within the array. When I was in engineering school, one of the first classes I took that gave me a real bear was my second semester of circuit analysis. So they would give you this circuit, and you were supposed to trace that signal through the circuit and develop an output. In most cases, in theory, after doing page after page of calculation, it looked like a nice lineup of those dogs eating out of the bowl. Then they would say, okay, now take it to the lab and test it, and it looked like everybody fighting over that same bowl of food. So what we do is we try to reduce those variables in practice. So we put it into our anaerobic chamber, also known as the antenna torture chamber. What that is a perfect lab environment. Of course, we don't live in that lab, but this gives us at least a starting point. When we talk to you about antennas, we have a place to start the discussion anyway, as far as what that beam pattern is going to look like to help you provide the proper coverage. This is an example of the two different types of omnidirectional antenna elements that you can find in most antennas. If you bust that radome off, you're going to see either a printed circuit board or discrete metal elements. A lot is going to depend on what you want that finished antenna to look like as to whether or not you're going to use a printed circuit board or a discrete element. You can obviously go, depending on the type of antenna again, and the gain and all the other characteristics that we've talked about, you might be able to get a more compact design using a printed circuit board, but that's not always the case. The third, is radome design. A big thing today is aesthetics. You can't just go and hang an antenna anywhere, particularly if you're talking about a hospital or a school. Number one, the architect may say, no, I'm not going to allow that to happen. Second, it might create a problem. If you're in a warehouse and the radome is too big and too bulky, you might get it hit by a forklift, someone trying to do their job. The size of the antenna is going to depend on the characteristics of that antenna. The higher the gain, generally the larger the element. And again, frequency, because an antenna element is usually a fraction of the wavelength, it's going to impact the size. The material of that radome is also important. If you're going outside, you want to make sure that that radome has a UV stabilizer in it. Otherwise, what's going to happen is a couple of years after you deploy that nice white antenna, it's going to look this ugly shade of yellow, and somebody's going to place a phone call and say, you know what, I really don't like the way that thing looks anymore. Can you please come and change it out? The color, again, it's going to be up to the architect or whoever has the final sign off on the design. I worked on a project, not necessarily with an antenna, but for an enclosure where people just couldn't decide on the color. So what we've gone to now is skins. Rather than trying to paint something or build the color into the plastic, we wrap it in a vinyl skin. If something happens, somebody doesn't like it, we take it off and we try another one. The back plane, of course, has to do with, the radiation patterns that we're going to end up with. If moisture is a problem, we might want to consider putting weep holes in that antenna because condensation now has a place to bleed out. If it doesn't, what you eventually end up with is a rain gauge. Again, aesthetics is going to be one of our keys, and it's so important, we put it first and last on this page. Next thing to consider is mounting. Like I said, I was a working engineer for a lot of years, and I've been in this business for a long time. What often happens is the last thing people think about, especially young, inexperienced engineers, is how am I going to mount this thing? Okay? These are the things we need to consider, indoor or outdoor. If we're going to articulate azimuth and elevation, are they both necessary? What do I have to mount it to? Wall, pole, ceiling, or combo mount? What type of material are we going to make it out of? And here's a big one. If it's going outside, what kind of wind load are we looking at? Otherwise, that antenna could turn into a flying saucer really quickly. What could be next? We're looking at tri-band antennas. We heard before about whether or not 900 megahertz was actually going to be implemented. If it is, we're going to have to build those antennas to match. But wait a minute, we've been talking about this all day. We have to wait for the radios. More importantly, we have to wait for the clients. so that our antennas are going to be able to speak as efficiently and effectively as possible. And since I have 5 seconds to go, don't forget to order your new antenna. Thank you very much.